Today is a new day. I am coffee ready to take on the next leg of this personal journey. In the prior video, 34 about events, we looked at how a question can drive us until we answer what is happening. In biology, for example, the question of how life works drove us crazy over several millennia, before finally resolving in the 20th century. And in physics, the DNA of reality still eludes and haunts us. This despite throwing everything along with the kitchen sink at the problem. We have even attempted to amend the fundaments of our reality to make progress. No matter what we do, we just can't seem to square a deterministic reality with a causal one, or in some other words, to unite properties and behaviors with a relatively simple Yocto object as was done with DNA. Our quiver just doesn't seem to have the necessary arrows to hit the bullseye. And by arrows I am referring to the rules we apply to reality, to either explain things or to see what is true about the world. We can't seem to hit the mark. The rules I am referring to were briefly covered in the last video. There were three types that I zeroed in on: definitions, generalizations, and causations. As a side note, I should mention that a single rule can fit under one or more of the types. It just depends on how it is used in an inference. By the way, I forgot to show the problem-solving summary screen filled out for the rules. I just needed to add a rule picture. One rule that I would like to introduce for this final video of 4 about events is a corollary to the second principle of object reality. Again, the second principle of object reality is an event happens. Correspondingly, the corollary is an event is a change of an object. To self-correct, I originally thought that the 2.1 corollary was an event changes an object. Even though true, this entails causation, and that is getting ahead of my skis. The intent of the corollary is more of a definition rather than a causation, so it had to be stripped down to the metal. That is one of the downsides of learning as I go. Mistakes happen. I am hoping that mistakes won't define these videos. Regardless, the corollary will become important for inertia, which will help lay the foundation for my physical model. The corollary will also place the requirements on any physical model that is proposed to explain inertia. Specifically, rather than loading all the responsibility on the infinite unreal for how a verse simply is, in other words, on something that is static and unchanging, a physical model should have a real object that can undergo change or is undergoing change. By the way, in the next video, which serves as a standalone addendum, I will present the sophistic principles of my physical model, as well as the model itself. I might as well take the bike I built out for a spin. It is time to circle back to the metaphysical assumptions for relativity, which was mentioned in the setup for this 4-video sequence. It is time to find the current home for our set of laws that fuel the principle of relativity, that pseudo-explain why we all see the same thing. As a starting point, we can explore a hypothetical using the somewhat recent proposal that there are many worlds, each with its own set of randomly generated constants and laws. Rather than explore the intricacies of the multiverse or the anthropic principle, we can use the multiverse hypothetical to uncover our underlying and partially hidden assumptions. It is a simple hypothetical, which was laid out at the end of the previous video. We can ask what would happen to a band of adventurers born and based in our universe that traveled to an alternatively ordered verse. In particular, would the particles and their properties from our world travel intact with the multiverse explorers, or would the laws of the foreign land govern the behavior of the exploring particles? The latter alternative is a bit disconcerting, because it could result in our adventurers vaporizing into primordial dust or imploding into a singularity. It is always best to read the fine print on the tour agency's website before taking off on a trip. Obviously, the answer to this question is way beyond our experimental or inferential reach. Even the question may be a silly flight of imagination. However, it does lead us to the additional question of, are laws dependent on objects in object reality, or are laws dependent on the background of a universe, and correspondingly the infinite unreal? Pick a side, and we can argue until we are blue in the face. It is like the optical illusions where background and objects can switch places in our visual interpretation. With a non-existent data set, we are left only with a priori arguments grounded on big T truths. I divert you to your local cafe to Google to your heart's content if you wish to pursue that avenue of spiritual inquiry. Still, we can learn something if we look at the question from a historical perspective, and how the game became afoot. The initial polarity came front and center when the positions of Aristotle and Galileo came head to head in describing the motions of bodies. Even though the issue was resolved long ago in Galileo's favor, it can illustrate the subtle differences in the two positions and what each position entails when it comes to how truth is pursued. If you want to find a parallel in another discipline, it is like the battle between preformism and epigenesis and genetics that we overviewed in the prior video. To illustrate the difference between Aristotle and Galileo, let's take a simple example and see how each position explains it. This is the Aristotle-Galileo comparison by a dummy version. Let's skip a flat stone across a mountain lake. Here is a simplified event-by-event breakdown of the complex event. From the initial throw, to the rock falling toward the water, to the rock skipping several times across the water, to the rock sinking, and finally to the rock coming to rest on the lake bottom. Surprisingly, even a seemingly simple event becomes complex when analyzed, when it is broken into its sub-events. First, we will look at the explanation from an Aristotelian perspective, then from a Galilean perspective. Just keep in the back of your mind the place we want to place our rules, in other words, our laws of science, with our intrepid multiverse adventurers or with their destination. Back to our diagram, which has the Aristotelian explanations of motion added. In an Aristotelian world, there are three elementary concepts needed to explain motion: natural motion, violent motion, and elemental viscosity. There are also Aristotle's four causes and the dynamic between actual and potential. While these concepts are important to understand Aristotle's metaphysics, that analysis can be set aside. It crosses into traditional metaphysics and is subject to philosophical interpretation. Interpretation is something we don't want to deal with when it comes to science, except, of course, when we need to lay the foundation for potential scientific revolutions. Back to Aristotle and his breakdown of motion. An example of a natural motion might be the drop of a rock toward the water after being released from the thrower's hand. Aristotle called it natural because the stone is trying to return to its elemental sphere, in other words, Earth. In this world, like attracts like. Coincidentally, this concept is very similar to like begets like in genetics. An example of a violent motion might be the skipping of the rock when it hits the water and deflects up. Aristotle called it violent because it diverts the stone away from its natural motion, its defining motion. An example of a viscous motion through an elemental sphere might be the stone sinking to the bottom of the lake. The water slows the stone while it is performing its natural motion. With these three fundamental motions, or some combination thereof, Aristotelian-based physics was able to explain how and why objects behave the way they do, for the most part. It purported to say what was really happening. This approach, based on common sense observation and deductive inference, which didn't ask too many hard questions, or try to stack its conclusions against hard evidence, held sway for nearly 2 millennia. Even though we tend to look back at Aristotelian physics as more mythology than science, there is one important central theme. For Aristotle, the world was primarily object-oriented. There were the 5 elements and the 5 elemental spheres: earth, water, air, fire, and ether. All earthly motion was a result of each object exhibiting its natural propensity to remain stationary relative to its elemental sphere, to return to its proper place, or to hinder other objects from doing so. Orbs, objects, and their properties could explain all of the motion in this world. Correspondingly, there is no such thing as a vacuum, or the absence of an object. Even time, in Aristotle's view, might have been considered an object-oriented phenomenon. In one recent Aristotelian interpretation, which Ursula Koop, a professor of ancient philosophy at Oxford, provides, time is the measurable change within the soul. As such, time is dependent on the soul, which is dependent on the body, in this interpretation of Aristotle. So assuming Aristotle would go along with the idea of a multiverse, which is unlikely, we could still guess how he would answer our science fiction hypothetical. Again, the alternatives were: 1, laws travel with our multiverse adventurers, or 2, the multiverse adventurers are subject to the laws of the foreign universe. Being object-driven, Aristotle would probably side with its laws infusing our multiverse adventurers. Said, the multiverse travelers would carry their laws and responsibilities wherever they went, no matter how they tried to shed them. They would be safe no matter which landmark they visited. Whew, one less adult thing to worry about. Now let's add the Galilean explanations to the same events that we looked at for Aristotle. Like Aristotle, Galileo provides three concepts, albeit slightly different, to explain all motion: natural vertical motion, natural horizontal motion, and forces such as friction. Briefly, natural vertical motion applies to the as-yet isolated universal gravity, such as an apple falling from a tree, or the moon orbiting around Jupiter. Natural horizontal motions refers to the newly abstracted concept of inertia. For example, a skater gliding across the ice, or a meditator standing stock still on the beach. Finally, friction correlates to a soon-to-be generalized idea of force. For instance, the push of a hand or the resistance a rock encounters when pulled along the ground. At first blush, the distinction between Aristotelian and Galilean physics may seem more like a semantics debate than a world-shifting revolution. For example, what Aristotle called natural motion, Galileo called natural vertical motion. Who cares if one philosopher calls it one thing and another natural philosopher calls it something else? Data, data. So really, what is all the fuss about? Traditionally, several areas have been pointed at to justify all the hoopla. For example, Galileo performed a generalization to suggest how bodies would move in outer space. This despite Galileo's inability to perform the actual experiment or even create a vacuum to experiment with. This was the basis for a new scientific approach, inference based on solid quantified experimentation that leads to a mathematical expression capable of prediction and verification. That, along with the discoveries it perpetuated, would have qualified Galileo for a Nobel Prize in physics, if they existed back then. Instead, he was rewarded with house arrest. No good deed goes unpunished, especially if it threatens established order or values. In addition to the scientific method, Galileo changed those events that required an explanation and those which do not. For example, natural philosophers after Aristotle spent a great deal of time trying to explain how air could push along an object such as a ball or an arrow when its natural inclination was to stop. Even though Aristotle was not too concerned with the phenomenon, it was called antipersistasis, or against remaining in the same place. By the way, the early Greeks were avid baseball fans. Then Galileo came along and said that such explanations for baseballs were not needed. Continuous horizontal motion was the norm, and it was the stopping or slowing, which was attributed to friction or intervention, that required an explanation, a cause. In implicit terms, if an occurrence can be expressed as a law, then no explanation is needed. It is a given. Flip-flops are common in revolutions, as they are at beaches. And like in our Ori example in the beginning of the prior video that made hot Jupiters the norm, create a mental bookmark for this point. All physical models have this division between things that require a cause and those that don't. The division will be explored later in the videos on causation, the third pillar of object reality. Thermodynamics notwithstanding, existence is another phenomenon that we assume does not require an explanation for its persistence. Take the example of the cheese slicers that both my mother and I cracked, as told in the prior video. There was a working assumption that something must have happened in order for it to crack and cease to exist as a whole. Of course, this is not a hard and fast rule. No rules are. There are always exceptions, especially in movies which thrive on novelty. Damn the exceptions, as well as the torpedoes. So far, we have highlighted two ways in which Galileo broke free from the Aristotelian mythology mold. The first was his scientific approach, and the second was his rearranging of phenomena that require an explanation and those that do not. There are others, but there is one more that is often overlooked, and that relates to our hypothetical multiverse adventures. We are finally getting closer to home. For Galileo, natural laws are written in the Book of Nature. However, the Book of Nature was not a literal book that could be checked out from a library. According to Galileo, it was instead a tome of God-decreed laws, scribed in big N nature. It needed smart mathematicians and not theologians to decipher. Theologians should continue to focus on interpreting Scripture, the Word of God, and leave nature to the scientists and mathematicians. According to Galileo's position, there was a division of labor, each with its own set of responsibilities and skills. This metaphysical position broke from the church, even though Galileo was trying to convince the church that he was not heretical. There was nothing extremely revolutionary about this approach to finding truth. It was a synthesis of many commonly held beliefs at the time. Great minds often bring together many old ideas cast in a different light, along with some new ones, to create a magic potion of insight and epiphany. Whether Galileo spoke literally or figuratively about the book of nature is anyone's guess. However, it bears a remarkable resemblance to one multiverse proposal, in which each universe began as a tabula rasa, and in which some chance event spun the wheel on about 26 fundamental constants. For example, no one knows why the gravitational constant, big G in Newton's law of gravitation, is what it is. For all we know, it could have been twice as big or twice as small. Our universe would have been remarkably different than it is today if the gravitational constant came up snake eyes. But we were fortunate enough to roll a 7. Of course, the big difference between Galileo's universe and a multiverse is that Galileo would say that God had a hand in setting up the initial conditions, in addition to carving the laws into the ethereal crystal. God, whatever its nature, would have wanted to get things right back then, since there was only one universe to play with. Now, according to many sophists, we have a number of verses approaching infinity. They are multiplying like cute bunny rabbits. Indeed, we have come very far in our journey. So where would Galileo squirrel away nature's art? I'm going to go out on a limb here and say in the kingdom of the infinite unreal, as a part of the tabula rasa. Unlike Aristotle, who lived in an object-oriented world, Galileo's world was more background-oriented. Take away any and all objects and the laws would still be in force, would still exist in some sense. In other words, our hypothetical multiverse adventurers would be subject to the laws of the verse they visited. Let's hope they weren't carrying anything illicit with them. In terms of history, one could metaphorically model scientific development as a slow Galilean chandelier, swinging between different worldviews, emphasizing either object reality or the infinite unreal as the preeminent reality. As a side note, philosophy has its own separate chandelier on the reality spectrum. However, science and much of society has chosen to abandon the metaphysics chandelier, and in effect has put it out to pasture to mix metaphors, labeling it irrelevant. That is a mistake. Ideally, there should be a dance between them, as some have recently maintained. I'm only beginning to understand the potential of such a dance, but it seems to be a give and take and give, in which the whole is greater than its parts. As it stands now, the relationship has become dysfunctional, where one side, the physics side, refuses to participate in the relationship for the most part. And why should it? It is making all the money, receiving all the notoriety, and basking in all the glory. Metaphysics has thrown the occasional historical scrap bone, such as when the reality of time is discussed. However, it receives none of the recognition or interest. From one point of view, it may seem that physics has outgrown the relationship, and rightly moved on, just as it has done with religion. There is some validity to that position. Philosophy does have its problematic and contentious, nitpicky side, that loves to create unanswerable questions and bicker ad nauseum over all the possible answers and their shortcomings. And that is perhaps understandable, given that metaphysics has had an identity crisis in the face of science's success. For example, in the last several centuries, science has made major headway in answering long-term questions, like what is the origin of the universe, what is the fundamental stuff of the universe, and what is the basic nature of the universe. These issues used to be the bread and butter of metaphysics. Still, it just may be me, but philosophy and even metaphysics has had a sort of mini-renaissance over the last several decades, at least internally. I guess I should have completed the philosophy doctorate program at UC Davis in the early 80s in order to be on the cusp of the resurgence. However, in a way, I'm glad that I ended up taking another path. I dove into the program for the wrong reasons. Also, I would probably have ended up teaching PE at some high school instead of metaphysics at a prestigious university. Not that coaching is an ignoble profession. I read the room when the room was gently ushering me out of the room. I partly attribute philosophy's turnaround in some forums to physics' foray into territory traditionally reserved for philosophy. Some upstart physicists have started opining about philosophy, reality, and its nature. Maybe it was because scientists don't appreciate philosophers telling them how to conduct their business. Old issues burn the longest and the hottest in a messy divorce. Still, for all intents and purposes, the old relationship is water under the bridge. Physics has moved on and has been cohabitating with a new partner, namely mathematics. And it has been an overwhelming successful union. That is one of the reasons mathematics has become the go-to tool for fundamental physics, and why physical models have been relegated to the rumble seat, used primarily in often misleading popularized versions of physics. Oddly enough, this partnership, in some physicists' view, has led to fundamental physics being frozen in place, no matter how beautiful the math may be. For example, the extended love affair with string theory has excluded many other promising approaches. Physics has gotten greedy. To bring back the chandelier analogy, physics has lumbered into the infinite unreal neighborhood and refuses to leave. However, like in philosophy, the times they are a-changing. More than several new and creative approaches have been popping up over the last few decades. A case in point, Lee Smolin has made some intriguing proposals. He has put forth the idea of time's reality and the Darwinian birthing and natural selection of universes. On a scale of 1 to 10 rebels, with 1 being extremely conservative and 10 being extremely revolutionary, I would put those proposals at around 6.5 rebels. It seems to have earned him a reputation as a maverick. So where does that leave us? Do we stay with what is over 300 years of tried and true? Or do we abandon our sailing ship because we have hit some doldrums? If I were a rational gambling man who bet the odds, I would go with tried and true. In other words, keep searching for the theory of everything based simply on mathematics, and don't bother trying to find the man behind the curtain. However, what is becoming more and more obvious to me in these videos, the approach I am taking is the latter, definitely dark horse. Maybe a whole army of ragtag rebels. In effect, I am betting on getting a royal flush in the next hand. Not the smartest of moves, like sacrificing the queen in the first 10 moves of a chess game. Sometimes the forbidden has a special fantastical allure. So in preparation to explore the sophistic foundations of my physical model and what it opens up, let's continue our look at the evolution of inertia to give an idea of the crazy that is heading our way. The goal is to tie up most interpretational issues with a messy bow. By the way, that is how my daughter looked when I had morning get ready for school duty. To that end, let's dive into Newton's bucket and the follow-on Mach's principle to converge some of the themes running through these videos. As a forward, please have patience with the following discussion. Things were a bit messy back in Newton's day when it comes to concepts like inertia and energy. In fact, despite improvements, they still are. Primarily, inertia remains a first principle that has yet to be explained, despite being an everyday occurrence. I have tried to remove most of the messiness and side issues in order to make a point. That approach has the advantage of driving the point home, but it may give a false impression that the progression of science and physics in particular is orderly, steady, and unambiguous. Nothing is further from the truth, which in truth evolves. Even though scientific philosophers and historians have put a lot of time and effort into rendering each natural philosopher's thoughts and assumptions, it is not always clear what each natural philosopher meant on any given day. Sometimes the philosopher had even made contradictory statements. Giants, no matter how huge, are human too. With those caveats, let's proceed. Newton's thought experiment was simple. Remove all objects in the universe except for a bucket full of water hung from a rope. Wind the bucket up and let it spin. Newton then asked Carnac the Magnificent what would happen. How would the water behave at the start of the spin and after significant spinning? Of course, the experiment is not as simple as it could have been, since the experiment requires a gravitational well, namely the Earth. However, there are other purer forms of the thought experiment that ask the same question and eliminate this difficulty. So for simplicity, we can keep it as Newton proposed. For context, Newton's thought experiment was in response to a position that René Descartes held. Descartes believed all motion is comprised of two forms, one illusory and one true. An example of illusory motion is the movement of a sailboat on the water. It is illusory because it depends on who is doing the observing. A windsurfer, depending on the direction, would either see the original sailboat moving faster or slower. Compare this to people sitting on the dock. All three perspectives, the sailor, the windsurfer, and the dock watchers, would record 3 different speeds for the sailboat. In other words, motion observed from other frames of reference is not universal and is therefore, relative. In contrast, the collision between two bodies provides an example of true motion in Descartes' scheme. It is true because the description of the collision would be identical no matter who did the observing, and therefore universal. For example, a cue ball striking the 8-ball would be absolute of proper motion according to Descartes. The velocity differential between the two billiard balls prior to and after the smack would be the same. For Descartes, true motion was based on the interaction between objects adjacent to each other. In one possible interpretation, true motion involves causality and illusory motion does not. It harkens back to the dichotomy between those things that require an explanation and those that don't. To put it into object real terms, true motion implies that a causal event has taken place, and correspondingly that something has in reality changed. That is one perspective on how things work. Still, Sir Newton was not satisfied with Descartes' analysis. Something was missing from the big picture, and his bucket proved it. As in so many a priori standoffs, two schools of thought developed, one based on the infinite unreal and one on object reality. Newton was in the infinite unreal corner. He believed that all motion was relative to an existing background, or what he called absolute space. In his view, the water surface would go concave because the water was changing direction relative to a single space, and the nearby bucket holding the water could not account for the concavity. For Newton, the spinning bucket demonstrated the reality of the infinite unreal, albeit as a wispy pseudo-substance unlike everyday matter. Yes, linear motion was entirely relative, as Newton encapsulated in his first law. However, the thing that made linear motion possible, in other words inertia, was dependent on this background blob. Further, absolute space was the cause of inertia, and his thought bucket proved it. As such, motion between nearby interacting objects, as Descartes proposed, was insufficient to establish true motion. Otherwise, the water would go concave the instant the bucket started to move. Newton believed that inertia was dependent upon something other than everyday objects, and that something had to be absolute space. Again, when you have eliminated all which is impossible, then whatever remains, however improbable, must be the truth. To quote Spock, who borrowed it from Sherlock Holmes, both giants in Western culture. In the opposite corner, the object real one, was Gottfried Leibniz, a contemporary of Newton, defining true motion relative to an absolute space, and thereby equating the infinite unreal with an existing thing, stuck in Leibniz's craw. The jump from a spinning bucket to an absolute background did not make deductive sense to Leibniz. It had to be something else. He would agree with Newton that the water would go concave only after the water had started to spin, but for a very different reason than Newton's. Like Newton, objects have inertia, but unlike Newton, the cause of inertia was inherent in each object. He called it vis viva, or living force. Today we call it kinetic energy. However, because of Newton's stature, Isaac's argument won the day. By the way, the Newton-Leibniz butting of heads also extended to claims about who invented/discovered calculus. Eventually, the truth about both issues came out. Neither was guilty of calculated plagiarism, and mathematically their different calculus methods were equivalent. He even used Leibniz's notation for differentials and integrals instead of Newton's. So I guess Leibniz had the final say. Despite the testiness between the two, as it turns out, both momentum, Newton's foundation of true motion, and kinetic energy, Leibniz's, are important concepts to classical physics. Both concepts were chiseled into equations, in which mass and velocity are the defining variables. Formally, each was partially right about the importance of the concept, and correspondingly, each was partially wrong about what defined true motion. They were not able to definitively establish or suggest a causal model to explain inertia and its role in the principle of relativity. Even with this whole, Newton's metaphysics held sway for about 2 centuries. It was not as suffocating as Aristotle's legacy, but sufficiently influential to blunt curious minds from asking inconvenient questions. To help his case, an ad hoc doctrine which Newton incorporated, and which was in line with Galileo's original vision, was the inability of experiment to distinguish different frames of reference. In Newton's extended version, there was no experiment that could detect linear motion relative to his absolute space. So why try? Just admit the bad part out loud and no one will challenge it. And most accepted that stance as gospel. That is, until the latter part of the 19th century, when cracks started to form, one philosophical and one experimental. Ernest Mach, in his Science of Mechanics, 1883, made the most vociferous conceptual attack on absolute space. He countered that no one could validly say a priori what would happen to Newton's spinning bucket, no matter what common sense tells us. Instead of absolute space, he maintained that the universe's collection of big masses, which we now know are organized into galactic superclusters, made more sense as the cause of inertia. As such, the water in Newton's spinning bucket would never go concave, since there was nothing in the universe to give it significant impact, except maybe coldness. Even though Mach proposed this as the best alternative to absolute space, he never went beyond this first principle and replaced Newtonian mechanics. As first principles go, it was at best wishing well thinking. At about the same time as Mach's rebuttal, Albert Michelson, a German-born American physicist, among others, was gearing up to use light as a way to detect linear motion relative to Newton's absolute space. It made perfect sense to try to detect the ether, the proposed manifestation of absolute space, since light should require a luminiferous medium to wave on. Finally, physicists were coming up with ways to detect motion relative to the ether, a motion that Newton thought was impossible to detect. Initially, Michelson perfected his interferometer to make more precise measurements of the speed of light. In 1887, the team of Michelson and Edward Morley, an American scientist and experimentalist, devised an experiment with enough precision which should have detected the movement of Earth through the ether. They tried to detect several motions through the ether. They slowly, gently spun their interferometer, resting on a slab of sandstone floating in a bath of mercury housed in a quiet, even-temperature basement. They tried recording the interference pattern over 24 hours, which would detect Earth's spin in the ether. They also tried detecting the shift at different times of the year, just in case there was a point in Earth's orbit that was stationary to the ether. In all cases, there was no detectable shift in the light interference pattern, which would denote Earth's movement through the ether. There were further machinations and attempts to save the ether hypothesis, such as ether drag, but all failed. More precise instrumentation, additional experimental test cases, and logical arguments prevailed over any and all afterthought attempts. The experiment confirmed the counterfactual that there was not a singular ether, which common sense had predicted. Sadly would be surprised, since that is how he makes his sleigh fly. The Michelson-Morley experiment was considered the most famous failed experiment, and even Michelson hesitated to accept it. Nature doesn't always conform with our manufactured model of reality. Along came Albert Einstein to make some sense of what nature was shouting at us. Interestingly enough, Einstein did not rely upon the Michelson-Morley experiment to guide him in his derivation of special relativity. Instead, he stood on the shoulder of James Clerk Maxwell, the developer of Maxwell's equations, which unified electromagnetism. Even though Einstein did not rely upon the Michelson and Morley experiment, he did rely upon Mach's principle to inspire and motivate him to develop general relativity. In fact, it was Einstein who coined the term Mach's principle. Despite Mach's principle being a muse for Einstein, when all is said and done, general relativity does not rely upon Mach's principle as a first principle. In other words, Mach's principle may be compatible with general relativity, but it is extraneous. In the face of the equivalence principle, which Einstein masterfully used to link standing on a spaceship with standing on the Earth's surface, one would think that Mach's principle would be a natural to explain inertia. However, inertia and gravity do not appear to have an apparent common cause. Gravity is the distortion of space-time resulting from mass or energy, whilst there is no such distortion associated with inertial mass that can account for a mass-resisting acceleration. Close, but no cigar. Inertia is a useful first principle, but we are still in the dark. So, what are we to do? How are we to storm nature's castle? If I may be so bold, I would like to huff and puff the reality chandelier closer toward objects and away from the infinite unreal, based on the physical model that is driving these videos. See, there is room for tinker toys in physics. Here is the proposal. Eventually, to be consistently oxymoronic, I hope to get to the point where each object is absolutely relative to itself, or at least it's to its own totality. In other words, each Yocto object will be the cause of its own inertia. It will be a synthesis of Descartes, Newton, Leibniz, Mach, and Einstein, but in a weird, simplistic, unforeseen way. In this view, the water will flatten against the wall of Newton's bucket, but not for the same reason Newton or Mach believed. Instead of moving relative to a single absolute background or to a mosaic of the universe's objects, each object establishes its own center relative to itself. Specifically, each object has its own background, and attempting to move the object relative to that background is what establishes the resistance to acceleration. Say what? I know this position smells like mumbo-jumbo soup at this point, but that is what will be the proposed source of inertia in these videos. It can also explain gravity, at least the downward force we feel while doing yoga on a paddleboard. Simply put, the proposed multi-purpose mechanism will be able to explain both gravitation and inertia. All we have to do is deconstruct space-time as the cause of gravity. Oh, is that all? As if saying it out loud makes it any easier. In summary, from 30,000 feet, skipping a lot of turns, barrel rolls, and dives, the evolution of inertia can be seen to have flown over the following sophistic highlights. Aristotle's object anti-inertia, in which an object abhors horizontal motion, and an object comes to rest relative to its classical element. Galileo's uncaused object inertia, in which an object remains at rest or in motion relative to another object. Newton's absolute background inertia, in which an object resists velocity change relative to a single motionless absolute space. Einstein/Mach's globalized object inertia, in which an object resists velocity change relative to the totality of all other objects in the universe. A to-be-determined single object inertia, in which an object resists a velocity change relative to its own totality, whatever that is determined to be. Of course, the last item, inertia as a property of an object itself, is more wishful thinking than reality at this point. If granted, however, we may come full circle with a twist, going from object to background, then back to object. The twist is the unification of object and background, further clarification of which will have to wait until the next scene, which I will explore in a self-contained addendum to these 4 videos. Keep moving, fast feet, fast feet. So to organize the evolution of inertia into a one-sheet cheat sheet, I will put the 5 highlights on the reality spectrum. Disclaimers. Where I put each natural philosopher on the reality spectrum is more subjective than objective. Also, limited real estate made precise placement kind of approximate. Still, it helps me keep my story straight. We start with Aristotle's anti-inertia and the extreme object real camp, in which an object's inherent properties control motion. Eventually, the edifice crumbled, so Galileo laid the law down about uncaused inertia in his Book of Nature, found in the library of the infinite unreal. To span the gap between the infinite unreal and object reality, along came Newton and his absolute space inertia, a synthesis of the infinite unreal with an actual object. However, absolute space didn't pan out, so Einstein replaced it with unreal relativistic spacetime and globalized inertia. It is progress, but unfortunately in the wrong direction when it comes to an abductive explanation of reality. We want a simple object that can possess intrinsically the property of inertia, like how Earth possesses roundness. Recently, there has been some promising candidates, but nothing so far has tied up all the loose ends, like Newton did with his 3 laws, despite their shortcomings. In a bit, we'll explore why Newton's laws are perhaps so compelling. Even though our journey is not complete, I can feel the force willing Galileo's chandelier to swing back toward an object-oriented world, toward little r reality, even if it is drawing us to consider outlandish, improbable fantasies as possible realities. Of course, the Galilean chandelier metaphor is a much simplified version of history. To extend the metaphor and make it more accurate, it will be like many busy bees pushing and pulling the chandelier in different directions at any given moment, and the chandelier is mounted in a rotating movie set. It is only when a significant number of bees agree on a single direction that movement takes place. Even then, the pendulum, given a discipline's framework, has its preferred resting place, which it eventually finds. If only my dog could find her sweet spot on our bed as naturally, without a lot of circling.